thank you for the introduction. Also, I'd like to thank the Fabio and the rest of the local organizing committee, Carmen, Lucas, Fabio, and also the students who have participated in the organization. By the way, excellent organization, really, excellent organization, so congratulations. But you know, this is my second time in Brazil. The first one was many years ago, in 1992, for the first Latin conference. You know, yesterday, Joachim Consultation, you know, said that Daniel was that. Unfortunately, we didn't meet each other. I think that I met you in some year later in Toronto. You remember me with Mark Gisbert at the same time? I don't remember exactly the year. It was in the winter. It was in the winter. So, anyway, I have been, you know, with Daniel in several places around the world. I really have good memories with you. And today I would like to comment a couple of, I would say, things about Daniel's personality. Okay? So, he's a modest guy. You know, let me explain this.
Can you hear in the back? Can you hear in the back?
Yes, no question about, you know, his excellent works. He's a good mathematician. You know, approve of this conference. Yes, but anyway, he's a modest guy from the mathematical point of view, and also, you know, for the personal one. The second one is about, well, he's a positive guy. You know, he always smiles. You know, I think he has the ability to solve any kind of situation, complicated or not, in a clever, how do you say, clever, elegant, and polite way. Okay, this is the second. This is the second thing that about you personality. So thanks, Jaime, here for giving me the opportunity to be here again in Brazil for this special group for Daniel. Okay, so I'm going to talk about polynomial. Okay, polynomial, local permutation polynomial. In fact, the main motivation, one of the main motivations to study this local permutation polynomial came from hypercube. This is an algebraic combinatorial structure. Oh, thanks a lot. Yeah, this is. So I said that this is this algebraic structure hypercubes. So there's a one-to-one map between hypercubes of order of prime power cube and dimension n, and particular polynomials in n variable with coefficient q, finite called local permutation polynomial. Okay, this is an elementary talk, by the way. So one of the main goal is providing a kind of dictionary between these hypercubes, the language of hypercubes, going to the hypercubes to the corresponding associated permutation polynomial. That's the main motivation, okay? Or one of the main motivations. Okay, okay, so it's very well known that any map from difficult n q can be represented by a polynomial in a variable coefficient q. Okay. In fact, this polynomial is unique if and only the degree of this polynomial in each variable is smaller than q. Okay, this is very well known, the Laplace interpolation formula, that in the particular case of finite cube, you know, this is this formula that I think implemented in Sage math and any other, you know, content related to local permutation polynomial that I really use. I going to illustrate in some computation about this polynomial. So, for the rest of my talk, all polynomials have degree smaller than q in each value. Okay? In particular, the total degree of a polynomial is at most n times q minus 1. Okay? Good. Okay, here is some new definition. Permutation polynomial in several variables. Okay? So we say that a polynomial f is a permutation polynomial in this equation. This yeah.
So the bottom.
Yeah, no. No.
Is the bottom. The bottom one goes from inside of the counter.
Anyway,
You need to use a repetition code.
exactly. So this equation has, exactly q power n minus 1 solution in the space into the exactly depends the q power n minus 1. Okay, for each a in the q. An alternative definition or related definition is the local permutation polynomial is a solid. So we take any variable, n, okay? And then taking any points, in f cubed to the n minus 1 and specialize this polynomial in this n minus 1 variable. And then we get a polynomial 1 variable. Okay? If this polynomial in 1 variable is a permutation polynomial in the previous set, then we have this called local permutation polynomial for any specialization and for any choice of the variable I. Okay, so, well, which is clear, by the way, is that any local permutation polynomial is a permutation polynomial. And the converse is not true. Let me show you an example. That's a very simple example. It takes polynomial x1 minus 1 plus x2. Okay, this obviously, obviously is no it's not local polynomial. Let's choose specialize the variable x2, and then and then choose for instance the point minus 1, and then this is not 1. Okay, and it's a permutation polynomial, which is clear that the solution here, has any element A in the Q has Q alignment of 1 solution, because choosing the I have linear, and then this Q alignment is 1 solution. But it's equal 1, local permutation polynomial and permutation, we are putting the same concept, okay? Permutation polynomial 1 variable. Okay, as Stephen as Stephen this morning, this is a very active local permutation polynomial at 1 variable. There are many solid functions. So, contrary to the case of permutation polynomial several variables, but they are only, well, the writer wrote a couple of papers, in the 70s, related to this concept, permutation polynomial, also appeared in his book, People Would Read It, and an application. So, to say, and Muller, Benny Muller, was a participant of this meeting, by the way, Benny Muller. He wrote, say, 2 or 3 papers, this concept of the permutation polynomial, but in particular, he was interested in well, I don't know, but the results are related to Q equal 2 and Q equal 3, basically. So, well, we can say, let me show you this the relation with this structure hypercubes, starting with Latin square. Okay? So a square for the cube is a dimensional right. You can cube such properties of a set add with cardinality q such that any element of f occurs q times in the lattice. It's the right. And it's a Latin square. Each element of f occurs exact once in every row and every column of f. Okay, that's it. So as one, is a square. Obviously, it's not Latin square because in this column, as you can see, here 0 twice. Okay, S2, is a Latin square. Well, Latin square, any Latin square is a square. Obviously, okay, the converse is not true. S1, it is no Latin square. There is one-to-one math, between as in the direction we talk, but the square of order Q, corresponds to permutation polynomial. A Latin square of order Q corresponds to local permutation polynomial. So that's very much to solve. Okay, what about hypercube? Anything else? Okay. Here is the name. Okay. In fact, this is the definition in that paper is a little bit more general. Okay? But let me consider attention in this definition. Okay?
That is breath misspelled. Doesn't have a C after students.
Really not all right.
Extra C on
There is a C at the end. That's all.
It's okay.
Anyway, so given to natural number n and q, non necessarily Q over print off. Then definition and set elements that called symbol. I have to give H for the Q at dimension n and type J between 0 and n minus 1 is an n-dimensional, right? Because Q and times with Q and symbol said that whenever any J coordinated at this set, each of the Q element appear in this right Q over n minus 1. So there's n equal 1, it's a permutation. If n is equal to 2 and j is equal to 0, we have an square. J is equal to 1, we have a Latin square. For n case n equal to 3, j equal to 0, call it cube. Okay, it's natural. Okay. When j is equal to 2, is a Latin cube. Remain right in the case j equal to 1. Okay, with this cube, next one 3, and and type 1. Anyway, a Latin hypercube is a hypercube by definition of a type of n minus 1. Okay. It's clear, by the way, that any hypercube at stage of type J is also of type 0 to n minus 1. Okay? Anything? I mean, it's clear. Okay, we have this very useful notation that we will use now hypercubes. But we didn't know the set of symbols by capital N. 0 to q minus 1. And the size, all right, in the lexicographic ordering, 0, 0 refers to q minus 1, q minus 1. Yeah, so on. So a hypercube can be represented, as n-dimensional array H with n plus 1, n plus 1 coordinates. The following says, in the cells, in x1, x2, xn, we store the symbol xn minus plus 1. Okay? But we use in this case, we have, z1 and z2 are Q. Okay. The cube, the cardinality of it is 4. And this is, the first column, we have 4 coordinates. Okay, 4 coordinates because we have the dimension this way. The first column, is represented by the last coordinate is 0. In the second column, the last coordinate is 1, and so on. It's such that, look at this, such that in the set, indices like 1, 2, 0, this is 0, this is, this is column 0, 1, this is 1, 1, column 3, this is column 3, we, store single 2, and so on. Okay. That's my representation as strategic uses in the anyway, so here is the by the way, C1 is Latin cube, and C2 is a cube of type 1. So J permutation polynomial. Okay. So well, we take this F is a polynomial in a variable with division in a finite cube. We take J, a number between 0 and n minus 1. Then we say that the F is a J permutation polynomial, or JPP, for all choices of the variable. Let me assume that we are the first one, okay? That will also generality. And then we take any point, in any point in the space F2 to the J, and specialize this polynomial in the first variable with this point, and then we get a polynomial in n minus j variable. This polynomial in minus j variable is a permutation polynomial. Same numerator, we say that this is a j permutation polynomial. Or here also is that F, well, it's called F is n minus 1 permutation polynomial. We see that F is a local permutation polynomial. F is a 0 permutation polynomial, and F is a permutation polynomial in the sense of the right. Okay. Again, here, any j permutation polynomial is also a k permutation polynomial with k, is between 0 and j minus 1. It's a k, okay? That's what it is. Yes, that's all. There's a 1-to-1 map between, hypercubes of order prime power and dimensional n, and times j with j permutation polynomial in the variable. It's elementary. Right? This is that's one element. The same problem. So, for instance, in the case. Ten minutes. Oh my God. So, yeah. Anyway, for instance, the idea was to tell you the performance of the code, that I can say it's smart, but they don't have time, so we help them first. Okay. So anyway, C1 corresponds to this polynomial, the previous one, to this linear polynomial, and C2, which is remember it was a polynomial with one permutation polynomial. So the question is, one of the main goals is to construct new families of J permutation polynomial, because in that case we have, for application hypercube, we have families of hypercube of type J. So, well, this is a theorem, saying that, well, this was proven by the writer in the case J equals 0, but can be generalized, say, in a spread of 1, for J permutation polynomial. These exponents are summed, 0 polynomial character. When, the sum runs over, F2 minus J coordinates, when this is not the first one. As a consequence, this theorem, we have the following theory that allow us to construct new families of J permutation polynomial, starting with polynomial one variable. Permutation polynomial one variable. Assuming that I'm writing G plus H, such that G contains the first n variable and H the rest of the n minus n variable. Okay? In that case, G is a J1 permutation polynomial, and H is J2 permutation polynomial, and then it's the sum plus one permutation polynomial. In the particular case that our final field is prime, that is equal Fp, then we have kind of the index. Okay, if F is J permutation polynomial, then for any J plus 1 plus J2 J, with J1 is smaller than n minus 1 and J2 is smaller than n minus 1, we have then either G is J1 permutation polynomial or H is J2 permutation polynomial. In particular, F is a local permutation polynomial if and only if G and H are local permutation polynomials. Okay. This is okay. Isotropy permutation polynomial. This concept, came from hypercubes. Well, we say that two hypercubes, A and B, capital A, capital B, are isotropic. There exists n plus 1 permutation so that we can transform, the hypercube A to the hypercube B using this permutation. Which is the correspondent, which is the associated definition and properties in J permutation polynomial. Very simple. I mean, given any permutation polynomial, one variable, then F is a J permutation polynomial if and only if this composition is again a J permutation polynomial. Okay, good. And the next one, we give a list of permutation polynomial, and then if we compose, in this case with the right hand, then F is a J permutation polynomial if and only if this composition is a J permutation polynomial. But the question here, computational problem that is interesting, is the following. You have to recognize that two polynomials, F and F bar, are isotropic. Given F, a given F bar, how to decide there exists, G and H equal, H1, Hn, at least a polynomial, the total n plus 1 permutation polynomial, one variable, such that we have this identity, this polynomial identity. Of course, we are looking, for efficient in terms of this size of U, and also, the number of the variable. Looking for polynomial time algorithm. Because we so, in fact, this is a very well-known problem for people working on symbolic computation, and it's called functional decomposition problem. It's a particular case. Okay, this functional decomposition problem. I think it's interesting. So let me continue. What about the degree? By the way, what about the degree of J permutation polynomial, the maximum degree? You know that any permutation polynomial in one variable has degree at most q minus 2. This is a consequence of the well-known admitted criterion. Okay. What about the situation with J permutation polynomial? Okay, here is the answer. Here is the answer. Okay, if Q is bigger than 3, so any J permutation polynomial has degree at most n times Q minus 1 minus J minus 1. In particular, now for local permutation polynomial, that is for J permutation polynomial of type n minus 1, then we have that the degree is at most. The question here is, okay, this is a sharp bound. In other words, that polynomial that achieved this bound, and that's yes. That's it, yes. Yeah. And however, by the way, however, those polynomials that has maximum degree, the coefficient are over the ground field cube. But you believe that there are samples of polynomial of maximum degree, polynomial of maximum degree, okay, so such that that's maximum degree. Okay, it's a conjecture. Okay, this is a recurrence polynomial, and we think, that's polynomial, this is transportation that permits 0 and 1, and obviously this is a J permutation polynomial, and then we conjecture that this is polynomial has, we have proven, for n equal 2, for n equal 3, and that's it. Okay, so let me finish with this transparencies. Well, look at them to so for the things. But well, it's very simple. No, Janet said, well, the problem in permutation of a variable is not construct permutation polynomial, because it takes any permutation, and apply the relative relation, and you have the polynomial. Okay, so this is basically the situation for permutation polynomial. Okay, but for local permutation polynomial or for J permutation polynomial, when J is bigger than 0, the situation changes dramatically. There is no formula. There is no computable formula to know the number of local permutation polynomial generate the J permutation polynomial. We don't have formula. Okay? That's the reason that to construct a family to get bounds, or to this of the bound, okay? But there's no so bounds. That's the reason that to construct new local permutation polynomial, general J permutation polynomial is an interesting problem. But let me finish just with a couple of comments about about the algebraic value, because this is the work of Gary Muller, for for Q equal 2 and Q equal 3, only for these two final fields. He provides a description of all local permutation polynomial in these two cases, okay, and given some relation, in the coefficient of the polynomial. And well, it is clear that the local permutation polynomial, as you can see, a local permutation polynomial with a point, a point, in the inner space f to the n, if n is the use of the coefficient of the polynomial f, as in the coefficient. So, local permutation polynomial is a variety with a zero set of a certain polynomial idea. And the question is how to compute, how to describe a system that generates polynomial system equation. This, although it's for this, it's a polynomial equation. Well, I mean, it's basically using the Rabinovic strip to describe, a system of generator of this idea. For instance, in particular, using this algebraic vanity, we are able to compute or reduce the Latin or the fault. It is by computing, the basis, and we get, kind of tabular system. Using this system, we are able to describe all that's it.
Time for a quick question or comment.
So there are any famous families of so where finite fields in one variable, right? So these can we get sort of analogs for variables?
Yeah, this is a good question. I think that there are many problems, related to this because J permutation polynomial. I think so, but I don't know. I mean, it's so positive, no? By optimism, no, but we can do many things in this direction.
Okay. Let's think there again. Okay, our next speaker is Thais Jamino from Universidade Federal de Santa Catarina. He talks about embedding covering three families.
Hello, everyone. Good afternoon. I'd like to thank the organization for such an amazing event. And I think the protocol is to start by telling you how I met Daniel, right? I was finishing my undergrad in computer science at UC, and there was this new guy there who was visiting us on this expo, and he was teaching a finite cubes course. I had no idea what a finite cube was, but all of my friends were enrolling in the course, so I decided to do the same. And there is only one thing that I heard from Custodio before joining the course, was that Daniel could transform a very hard concept into something that was easy to understand. And that was absolutely true. After that, I joined my master's, and Daniel was still around, so he helped me together with Custodio to pick a subject, a research subject. And Daniel presented me to Lucia, which was a game changer because she ended up being my co-supervisor in my master's and my supervisor in the PhD. And during my master's, we did so many research meetings, and we ended up writing a paper together. And this was a special paper for me because it was my first paper in a journal. And after that, I moved to Ottawa to do my PhD with Lucia, and Daniel was always around. So he was in my comprehensive exam, he was part of my committee, also part of the committee in my PhD proposal. And I made sure to enroll in every single course that Daniel was offering. But here's the thing, I've already finished all the mandatory courses, so I was just doing it for fun.
Yes.
And the other thing is that I would have to cross the city to go to Carleton U to do courses. Everything called Ottawa. So I guess that maybe says a little bit about his teaching skills and why we love to watch his work. Nowadays, I'm back at UFSC, and I made sure to introduce to Daniel many of my students, especially those ones that are interested in a math that goes way beyond what I can do. It's really fun to be around Daniel. He's kind, and he's very generous with his ideas and his time. He always finds time to meet us. So, now, cover frequencies. I like to start this off by telling you a little bit about combinatorial, which is one of the applications. Combinatorial group testing started during Second World War, where they wanted to test people for sick days, but they didn't have enough resources to test each person. So the idea was to combine blood samples and test these groups, these mixtures, instead of testing each person. And they did this in a way that the groups that passed the test, they determined all the good elements, which means that the bad ones are the remaining. So here in this example, groups 3 and 4 passed the test. So all of these guys, yellow, blue, green, orange, and purple, they're all healthy or good. So the reason why these two failed, I know it seems like magic, but it's not. It's combinatorics. And we can represent this using a binary matrix with some special properties. So columns are elements that I want to test. Rows tell me which ones I'm testing together. And the property that we are looking for is called D cover free. So this is a D over 3 family with, it allows me to identify up to D bad elements with T tests and M elements. The property that we want is the following. No element should be covered by the union of any other D, especially if these D are the bad ones. All the good elements should be this one. So I'm going to show you an example here. This is a one CFF. So no bad element should cover the other. And let's think, for example, that element bad one. So test 1 and 2 will fail, but every other good element or person will be in a good test. So this is a one CFF. I only did 4 tests to test 60. Here I have a 2 CFF where I'm capable of identifying up to two bad elements. For instance, if 1 and 2 are bad elements, they will fail test 7, 8, and 9. They save all of the good elements. But this are any 2 columns that you pick. So, for example, 4 and 12, all of the good elements are in at least one good test, and so on. If you prefer a set system definition, I have one for you. We can consider columns as instance vectors of subsets of a set X, and the problem and the characteristic that we are looking for is that the union of these subsets should not cover it. So this means that we have this one extra test that saves this guy from these bad guys that we have. So no element is covered by the union of any other. We have bounds, we have constructions for these objects. When d equals to 1, we know we can use finite set systems, and it's quite good because we have only log n tests as n elements. For d greater than 2, the best lower bound that we know is this one. So we need at least d squared log d times log n tests. We have several constructions that can. So we have about d squared log n tests. Many constructions, but this is a huge conference. I guess I should talk about a construction based on finite. And I'm so lucky because this is my favorite. It has so much, so many properties in it, and I'm going to show you. So in this talk, I'm going to talk a little bit of covariant families on cryptography. This is the main reason why I started looking at covariant families. Later, I'm going to show you that CFFs, the way that we know them, they do not work for dynamic applications. So we need a new definition, a new construction. And I'm going to show you how we can do that using finite. And some applications in cryptography. There are so many, actually many more than these ones. I'm not going to go over there, but I want to show you these 2 here. One in digital signatures and another one in distribution. If you are interested in learning more about this, applications, constructions, bounds, there is this we just found it that has constructions, applications, generalizations, and okay, let's go to the first application, fault tolerance in aggregation. A digital signature allows us to guarantee integrity and authenticity of digital documents. So we have here. I'm going to show you a signature algorithm. So the signature algorithm will grab a digital document and it will generate this extra piece of information, which is the digital signature. Later, we can use